All right, this is geometry. We're reviewing chapters 8 and 9. 8 on transformations, 9 on area. Don't forget to smash the subscribe button, like it, and leave drop a comment. All right, a good one, a kind one. Okay. All right, so chapters 8 and 9. First, transformations. All right, the transformation sheet is going to be important, and this practice, okay, for transformations. All right. So make sure you're looking over this. When we well, remind me of the transformations. Go ahead.
Rotation.
A rotation. What is a rotation?
You rotate the object.
Okay, I rotated about some degrees. Okay. Is there also another thing called a rotation? Is there something else by definition that's a rotation?
You don't know. It can be a rotation inside the object.
It can be two reflections through
Two parallel lines.
not
Oh,
intersecting lines. A rotation, right, is two reflections through lines that intersect. All right, so a rotation is one. What's another transformation?
Translation.
A translation. What's a translation?
It's where you move the object without changing the angles or it's an isometry.
It is an isometry. A rotation is as well. How does a translation differ from a rotation? Yes? Yes? Correct. That's right. So a transformation, what's on the top stays on the top, and what's on the bottom stays on the bottom. You're moving it up, down, left, right, or up and right, or down and left, right? But with a rotation, the image is not always the top, right? Because we're literally rotating it, okay? So it's literally moving it up, down, left, or right. Now, what is also by definition a translation? It's a
Reflection
through
two parallel lines.
through lines that are parallel. So two reflections through lines that are parallel. All right, what's another one?
Dilation.
Dilation. What's dilation?
Not an isometry.
It's not an isometry. It either gets bigger or gets smaller. But what stays the same? The angles stay the same, right? All right. And then we have reflections. We talked about reflections, right? In terms of rotations, if there's two of them, or translations, if there's two of them. All right, and we can reflect if I have a Cartesian coordinate system and I have a triangle. I can reflect across the y-axis, or I can reflect across the x-axis. How do the coordinates change when I reflect across the x-axis? What coordinate changes? The x doesn't change. The y becomes the negative of it, right? So if I have an x, y coordinate and I reflect it across the x-axis, this becomes x negative y. Make sense? Got it? That's on your transformation sheet. Now, yes?
If you started in the fourth coordinate and reflected it like up, then would it be negative y to positive y?
It would still be x, the opposite of y. But the opposite of negative number is a
Yeah.
positive number. So it doesn't matter, actually. All right, now, if I reflect, okay, this is called a vertical reflection, okay? Because I'm reflecting it vertically, and the vertical coordinate changes. Got it? So if you can remember, this is a vertical reflection. The coordinate that changes is the vertical one, the y. All right? When I reflect it across the y-axis, I'm reflecting it horizontally. So because that's called a horizontal reflection, then what coordinate changes? If it's horizontal, the horizontal coordinate, the x. So if I go from quadrant 1 to quadrant 2, then it becomes negative x. The y coordinate doesn't change. All right? All right, so you'll need to know the reflection rules, and you'll need to know the rotation rules on this sheet. The reflection rules and the rotation rules. Got it? If I had to, I'd make myself note cards and I'd memorize them. Boom, go through them. Make sure you know them. Okay? In fact, y'all should do maybe a Quizlet to help future classes, or maybe look for a Quizlet. In fact, if y'all find a Quizlet, y'all need to tell me. That just came to my brain. All right. Now, let's look at the review practice. All right? All right, we have a hexagon. You see the hexagon? And it's labeled. The midpoint of each side is labeled, and every vertex is labeled. Everybody see that? Got it? Okay. Now, if I just wanted to figure out the angle of rotation, could I figure out what each one of those, what the angle is between each one of those dotted lines? So OF to OG. Could I figure that out? The answer is yes. And I can just count the lines. So somebody count the lines. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines. Somebody agree? I would take all the way around, divided by 12 segments to get 30 degrees. So that each one of those sections is 30 degrees. So if I rotate OF to OG, then I've rotated it 30 degrees. Got it? If I rotate OF to OI, then I've rotated it 90 degrees. 3 times 30. Are you with me? If I rotate, okay, I'm not gonna be overly concerned about positive or negative angles. Okay? Because if I said, I will eventually be very concerned about positive or negative angles. Because rotating counterclockwise is a positive angle. Rotating clockwise is a negative angle in trig. Okay, but I'm not going to be overly concerned about that with the transformations. Okay? So if I said in a question, through what angle is OF rotated to OI, what if you went the other way? Like, instead of going OF to OI, if you went this way and gave me that answer, I would take it. The answer key probably would not have that answer, but I'm going to look logically at your work, okay? All right, now, let's look at number 1. It says, find the angle of rotation about O. So O is the center of rotation. That maps PQ, do y'all see PQ? That line segment to MN. So we want to take PQ and rotate it all the way to MN. So you either decide I'm going Q to N or P to M. The first one to the first letter or the second one to the second letter. Does that make sense? Or how many times do I have to move that segment? 1, 2. So 2 is how many degrees? 60 degrees. Does that make sense? All right, now, what if I were to ask, what is the image of ON? So ON is the original. All right, what is the image of ON after a rotation of 120 degrees about point O? So if you take ON and rotate it 120 degrees, how many times do you have to move it? 4. And so which one would it be? OJ or OF, right? I would take either one until we get to trig. And then it's a different story. Got it? All right. Does everybody understand that?
If it asks for, because it's asking for 120 degrees positive, it would be.
It would be OJ.
Yeah, okay.
If we're in trig.
Okay.
This is not really trig.
I just want to get used
But
to
yes,
it.
yes, you can. Okay. All right. Now the right figure is an isometry to the left. So now we're talking about the coins. Are their orientations the same or opposite? And what type of isometry is it? So are they the same or opposite? They're opposite. So what kind of isometry is it? It's a reflection. Everybody understand that? Easy peasy. All right, look at number 4. The original is CDEF. Y'all see that? And the image is QRST. Maybe not in the same order, right? All right. If you were to be asked, what is the image of CD? Then you look to CD and find its same side in QRST. What do y'all think it is?
TQ.
TQ. Everybody see that? What's the image of angle D? Angle Q. All right. Everybody with me? Does everybody agree? Got it? What does this do? What's the transformation? What do you think it is? How do we get from here to here? Is it just a rotation? It's got to be a reflection, then a rotation, right? It reflects, then rotates. All right. Number 6 on page 2. So if we're saying, it says name the translation image of ABC. So they're saying ABC is the original. But what is the image after it's reflected over line T? All right, so that's where we're going to start. What is ABC reflected over line T?
OPQ.
OPQ. And then reflected over line R.
UVW.
Yes, it should look exactly like the first. So the first to the last would be a translation, but it's 2 reflections through parallel lines. Everybody follow me? Following that? Okay, now we're talking about rotation symmetry. On number 7. All right. What's the end-fold rotation of that image? Do y'all remember end-fold rotation? It means how many times I can rotate the image so that it looks exactly the same.
3.
It's 3-fold. So we have 3-fold rotation symmetry. All right? Does everybody see that? All right. So what would be the angle through which I can rotate it once so that the image looks the exact same?
120.
That's correct. It'd be 120. You take the 360 and divide it by how many times you can rotate it to see the angle of rotation through which we get a symmetric image. Does that make sense? Everybody hanging with me? So the answer to 7 would be 120 degrees. I can rotate it at 120 degrees. All right, now we have a spinner. And when we spin, we want to find the degree of rotation that maps J to D. So we're going from J to D. First, let's decide what would be the angle from going to like J to I. What would one movement of the spinner be? How do I find this? 360 divided by what?
10.
10. So 36 degrees. That's correct. So now to go from J to D, what would that be?
156.
So you multiply 36 times 6,
That'd be
6, 18, 2, 16. Is that what you said? Okay, would another answer be acceptable to me?
Yes.
Yes, we could go, it depends. If I hit the spinner that way, or do I hit the spinner this way, right? So I could go J to D, but that would be 1, 2, 3, 4. So I could have multiplied it by 4, 36 times 4. Okay, I probably would take either answer. But rotating this way is positive. Rotating this way is negative. But I'm okay if you do both ways positive until we get to trig. Okay? All right, number 9. We have a 3-dimensional object on a 2-dimensional plane. So imagine it being a 3-dimensional object. Does it have rotational symmetry about a line or reflectional symmetry in a plane? So, does that car have rotational symmetry or reflection symmetry? Reflection through the center of it. Smack dab through the center of that police car would be reflection symmetry. All right, here's the next one. So it says, draw the image of ABC reflected in the x-axis. So right here, you do it. Reflected across the x-axis. If you reflect it across the x-axis, what kind of reflection is that? It's a vertical. You reflected it across the y-axis. Reflected across the x-axis. So it should go, what quadrant should it end up in? Quadrant 2. And you would label the image A prime, B prime, C prime, so that I know which vertex goes with what original. What's the image of the original? So A apostrophe, B apostrophe, C apostrophe. Remember that? All right, so it should look like this. You did a translation. You see the difference? This is what it should look like. So it goes this way to that way, right? Here to here is a reflection. A translation would just be top is still the top. But with a reflection, the bottom becomes the top and the top becomes the bottom. All right. Now, you have what appears to be a rectangle. And I want you to rotate it, and I want you to rotate it clockwise 90 degrees about the origin. I only want you to do 90 degrees about the origin. So rotate it clockwise 90 degrees about the origin. Do y'all have your little sheets? Your reflection sheets. Oh, here it is, Paula. I mean your rotation. Sorry, it's your rotation. So I said do it clockwise 90. That's at the bottom here. So you have xy becomes y negative x. xy becomes y negative x. So you have to find xy. What's one of the coordinates? 4, 3. Is 4, 3 one coordinate? Of the top, do y'all see that? 4,
All halves.
3. Well, it's counting by twos.
Oh. Yeah, I knew that.
4, 3. You did counterclockwise, which is okay.
Was it asking?
I believe I said clockwise. Did I write clockwise? I wrote clockwise, yeah. It didn't say it in the problem. So, because it's counting by twos, this is probably 4, 3, right? 4, 3 becomes 3, negative 4.
Do it clockwise.
Yeah. And we'll have to stop here. I want to say one other thing about rhombuses. Do y'all remember rhombus? Don't forget a rhombus. What is the area of a rhombus? It's 1/2 diagonal 1 times diagonal 2. If this is 8, that's 8. If this is 5, that's 5. If I don't give you that, and I just give you this, then you calculate that using Pythagorean's theorem. You calculate the leg using Pythagorean's theorem.